you can see in the first problem here, we're sort of revisiting the weighted average idea. Oh, hang on a minute. I've got people who are getting kicked off and back on. So the weighted average idea, remember that this is a carryover from a previous chapter. I gave you the percentages that went with the particular mass. Keep in mind that you have your mass, for instance, the 155 gram ones were 20% of the population of the tomatoes. We had 38%, 15%, 27%. The most common mistake that I saw made was people did a division. Weighted averages have no division step. So by the time you multiply across and you do your masses times your percentages by moving your decimal place, and then you total them up and you get a weighted average of 169.8. Note that since 38% was the highest percentage popularity, basically, for your data there, your value actually ends up probably somewhat closer to 160 than it does to any of the other values. Then we move on to utilizing grams and moles and molecules or atoms. For strontium, when you look up strontium on the periodic table, you have 87.62. And 43 divided by that should give you 0.491 as your number of moles. Going in the opposite direction, if you are given moles for the fluorine and you are calculating grams, this one's not a division step, this one is a multiplication step. 19 is the atomic weight of fluorine. When you multiply the two of those together, your moles cancel out and you get 2.85. For the bromine problem, this one must be done in 2 steps. Now, I stopped in the middle and gave you an answer in the number of moles. You could have simply linked the two of them together and done the math all the way across. It should not give you a different ending answer. Take your 6 grams, divide by the atomic mass of bromine. I got 0.075 moles. Then I multiply by Avogadro's number, 6.022 times 10 to the 23rd. And you get 4.5 times 10 to the 22nd. I saw a few exponent errors. Beware, depending upon what brand and what model of calculator you use, don't use the caret key. That is not what the caret key is designed for. This is a common error. If you have a TI brand calculator and it's one of the upper level models, one of the second function keys has 2 capital letter E's. This is what you're supposed to be using in order to invoke your exponent function. I loathe TIs. They're counterintuitive because all of the useful functions are second and third functions instead of first functions. So I have lots of gripes with TI calculators. For tin phosphate, keep in mind that since you have a set of parentheses in this molecule, you need to multiply the stuff that's inside of the parentheses times 2. That way I end up with 3 tins, 2 phosphorus atoms, and 8 oxygens. And I kind of did my totals across there and then added them down. So you get 546 grams per mole as your molar mass. For copper cyanide, note we have 3 atoms present. We have a copper, we have a carbon, we have a nitrogen. copper cyanide, copper 1 cyanide, being a fairly straightforward molecule. 63 for copper, 12 for carbon, 14 for nitrogen. Your molar mass is 89.5. Then you multiply by your quarter of mole, and you would end up with 22.39, or if you rounded it, 22.4 grams. The one on the bottom is another one that you're going to have to kind of do in 2 steps because it's a molecule and not an individual element. We've got a potassium, we have 2 carbons, we have 3 oxygens and 3 hydrogens and 2 oxygens. Look up your masses, multiply them as needed. You have a molar mass of 98-ish. So 50 times 1 over the 98.144 should give you 0.509, or if you rounded it, half a gram, or half a mole rather. Mass percents must be done for all of the atoms of the element in that particular molecule. I have 2 potassium, 2 chromium, 7 oxygen. Again, there's sort of a method to this that I went through in the notes of if you set them up such that when you are multiplying across, you've kind of already done about half your math, because 2 atoms of potassium will give me 78.2. And my total molar mass was 294. So each time I'm putting the mass of all of the elements or all of the atoms of that element on the top, divide, multiply by 100 so that it's not a decimal, so that it gets turned into a percentage. And that will give you 26-ish for the potassium, about 35-ish for your chromium, and 38% for your oxygen. Then we move on into empirical formulas versus molecular formulas. Again, this is kind of a multi-step process. First, you need to turn percentages into grams, which basically just change the symbol. Then use your numbers from the periodic table, 12 for carbon, 1 for hydrogen, 14 for nitrogen. Do your divisions, that will give you moles. But because this is a molecule with 3 different elements in it, I need to divide by the smallest number of the 3 moles, which ends up being the 1.96. You don't get all whole numbers out of this, because if you look at the carbon, the 4.87 divided by the 1.96 gives you basically 2.5. We talked about this. This is not a just rounded moment. You must multiply by 2 in order to get actual whole numbers. That gives me 5 carbons, 14 hydrogens, and 2 nitrogens. If you test it, if you add up the weight of 5 carbons, 14 hydrogens, 2 nitrogens, you will find out, excuse me, that you are pretty much right on 102. So the value there, or the formula, is both the empirical and the molecular formula. I gave you a similar one that started with grams instead of percentages. Same basic premise. This one didn't have any halves in it. Your sodium, your aluminum, your fluorine. Take your grams, divide by your table weights. We get 1.43 for the sodium, 0.48 for the aluminum, 2.85 for the, excuse me, the fluorine. This is another one where you got to pick the smallest one. In this case, your 0.48, which was your aluminum, divide each one. And like I said, this one didn't have any halves in it. Everything was really pretty close to being a whole number. 2.97 rounds easily up to 3. You have 1 for the aluminum. 5.9 is still pretty close to a whole number, so you can call that one 6. That gives you Na3Al F6. Then we moved on into the solutions, which was the final segment of the chapter. If I have calcium nitrate and I want to make 250 mils of 0.6 molar, I got to do a couple of different things here. One, I actually need to know what my molar mass is. So calcium plus 2 nitrogens plus 6 oxygens. That will give me 164 as my molar mass. Multiply your 0.6 molar times your quarter of a liter. That gives you 0.15 moles. Then when you multiply by the 164, it will cancel out the moles and give you 24.615 grams. Going in the other direction. This one, starting with the grams and a volume and finding out what the molarity is. So you've got 55.85 and then 3 times the mass of chlorine, gives you a molar mass of 162. So this one, divide first, 35 times 1 over 162. That gives you 0.216 moles. Make sure you have moved the decimal place on your milliliters so that you actually have liters. Finish out your division, and you get 0.539 molar. And then the last one, the last couple. 13 is a dilution problem. M1V1 equals M2V2. So I started out with 7.5 molar hydrochloric acid. I don't know how much of the concentrated stuff I need yet, but I want to dilute it down to a half a liter of 0.115 molar. So multiply the two things on the right-hand side together. That gives you 0.0575. Move your 7.5 down underneath as an algebraic rearrange. That gives you 0.0076 liters, and it does actually say how many milliliters, so you are supposed to move your decimal place before you report the answer, and this gives you 7.6 mils. And the last one has both a solute and a solvent. We have talked about the fact that water is 1 gram per liter. Therefore, 1,000 grams plus the 89 go on the bottom. Do your division, then multiply by 100, and you get 8.2%. Some people did not add the solute to the solvent on the bottom. Questions about homework?
Yes, really quick on that last one. I actually worked it out both ways because I wasn't sure whether I should assume that it was already dissolved or will be dissolved since it's just present tense. How do we just always assume that it's not yet been added?
Unless it says mass per volume, you have to assume that both things are present in the denominator part. You can't assume that it's only 1 liter. The only time you're only putting liters on the bottom is when you're doing molarity. Molarity is kind of a different mechanism than percentage by mass. So assume that both of them need to be added together. That's kind of a standard method.
Okay.
Other questions? All right. I am going to try something that my big kid and I were tinkering with over the weekend. We're going on a road trip. I'm gonna actually use my chalkboard because I want to show you an example. We'll see if I can get this to work. Oops, that's upside down. It would help if it was right side up. Try to make it high enough you can see the whole chalkboard. Still not high enough. I think I did something wrong. Oh, I didn't realize you'd squash that. No. Okay. Scoop. Actually, I need to grab my sheet of paper.
Yeah. Okay.
Anyway, yeah, like I said, we're kind of messing with this whole mechanism here.
There you go.
All right, that's not too bad. So
Do you
this
want it
is
further back?
no, that's fine. This is an example that's actually in your notes, but I really just like the idea that it's kind of hard for me to like draw arrows and all in any other way. So I want to do this one precipitation problem on the board here so you can actually kind of see the method that I'm using with it. This one is called the in-class problem, and I'll pull it up later after I'm done with that as a screen share. But I kind of want to do it so that you can actually see me doing it. So the thing that it's asking you to combine is NH4 in parentheses with a 3 and a PO4, and we are combining it with cobalt iodide. So those are your two aqueous solutions. And we're going to determine what they make in terms of a precipitate and whether or not you have certain things that drop out as spectators. So these are the two things that I want to start with here. I want to start with the idea that I've got ammonium, which is a +1 charge. I've got phosphate that is a -3 charge. I've got cobalt, and I've got iodide. So I'm going to split it into two halves there also. Actually, let me go back and erase these. So first and last. Remember I said it kind of looks like foil? The idea here is that you're going to try to stick the first thing to the last thing, and then I'm going to do it in reverse to a degree. I'm going to do this, okay? I'm going to do third and second. So if I start writing with the things that this might turn into, this I have to go, it requires me to go back and think about my charges. NH4 has a +1 charge. The iodides do not stick to each other, okay? They're actually kind of looks like this. You have a cobalt in the middle, you have an I over here, and you have an I over here. So it splits here and here, and that way you get kind of 3 separate pieces out of it. But the iodides are -1s. So Ni is one option that I might get. And then the cobalt and the phosphate, but I gotta think about my charges. My charges are kind of messy here. Since my cobalt is a +2 version, because it's stuck to 2 iodides, and I know from looking it up that my phosphate is a -3, I can't actually use just one of each. I actually have to deal with the fact that I'm going to need a couple of each one. I'm going to need 3 cobalts, and I'm going to need 2 phosphates. These are +2s, these are -3s. So I know it's kind of written vertically, but this is your molecular reaction, and it's not balanced yet either, because 3 ammoniums, I only had 1 phosphate, I need at least 2. I'm going to go back and put a 2 here. Well, that means I'm going to need 6 NH4s, so I'll put a 6 there. I had cobalt iodide here. I've got to have at least 3, so I'm going to put a 3 there. Actually, that should work. 2 times 3 gives me 6 NH4s, 2 phosphates. There's my 2 phosphates. 3 cobalts, 3 cobalts, 6 iodides, which match up with my 6 iodides there. So this is my balanced molecular equation. What if I split it apart? What if I start making a complete ionic out of it? Remember, everything that did not make a solid splits apart, which means I need another piece of information. I need to know what my solid is. First, I'm going to look at this molecule. This molecule starts with an NH4. One of the rules says anything with an ammonium is automatically aqueous, not solid. So this one's aqueous. But one of the last rules says most things with a phosphate are not soluble. This one is your solid. So if I start splitting this all apart to write my complete ionic out of it, I'm going to get 6 ammoniums. I'm going to get 6 iodides. I'm going to get 3 cobalt plus 2s and 2 phosphate. Again, I'm kind of doing this vertically. Everything that did not stay stuck together continues to be an ion. So this thing and this thing, I'm going to have 6 ammoniums, 6 iodides, but this is my one that is not pieces. It's got CO3PO42, and that way it's not an ion. Now I go back, I actually have colored chalk, and I can show you how the spectators go away. This one is charged, NH4 plus. This one is charged, NH4 plus. Those drop out, they're spectators. 6 iodides, 6 I minuses, 6 I minuses. Those drop out. So remember I said that there is a pattern to doing your net ionics. I'm going to take what's left over. So here is my net ionic. Positive thing, in this case, multiple positive things, 3 cobalts and 2 phosphates. And then you only have a single item over there on the right-hand side, and it gives you your pattern. Positive thing, negative thing, solid. All the net ionics that we are seeing that actually made a solid precipitate only have a single product. So I thought maybe kind of going through this, like I said, it's in your notes, but I thought kind of going through this by a different method might prove sort of helpful, because that way I can kind of show you where things are going as you're writing things out. I'm going to actually flip back over to the other stuff here in a moment. So it requires me to detach my webcam and carry it back over to my desk. There are some actual positive qualities. Oops, I'm upside down again. Positive qualities about actually having a webcam that is not part of my computer, because it means I can do some other things with it. Last spring when I was doing, we can't get that stick. Last spring when I was doing labs, I was doing demos with my webcam. Stick. Yeah, I know, and I can't get it to perch. Now it's like staring at the ceiling. Yeah, I know. I'm probably making you dizzy. I think I finally got it back. So did seeing the precipitation reaction stuff kind of sort of in real time, was that helpful?
Yeah.
Because it's a sort of a different method than just kind of staring at the instructions on the screen. And I might do that when we get around to the redox stuff too, maybe.
I do like that more. It's like easier to follow along.
Yeah, it is. It's like, okay, I'm used to doing things a certain way. I'm used to doing explanations that are kind of a little more interactive. So yeah, trying to do all this digitally is just frustrating. Anyway, let me pull open my file for that then. Of course, this also really requires that I find the right file to open. Share screen. All right, so here's the one we were just looking at. Like I said, you can go back and look at this part too, in that it shows you, okay, combine these two things. And then in the notes here, I actually didn't show you the complete ionic version. I just did the molecular version and the net ionic. You don't have to do the complete ionic. It's not a required step unless the question asks for it. But it is often a useful step kind of along the way. All right, we're going to switch gears a little bit. Talk about acid-base reactions. So we did acids when we were doing nomenclature. One of the things we said is, okay, if it starts with an H and it's not a water molecule, we then can make some certain assumptions. All of the ones this semester, if you see H's at the beginning, we are going to make assumptions that they are acids. Now here's a couple more, we'll call them buzzwords. If it starts with one hydrogen, this is referred to as monoprotic. Remember, protic kind of implies protons, because a naked hydrogen, because hydrogen itself is just one proton and one electron, so if you steal the electron, all you have is a naked proton. So this is kind of why they call it monoprotic. Diprotic, 2 hydrogens. Triprotic, 3 hydrogens. In inorganic chem, there are no things above triprotic. There's no quadra or tetra or anything like that. I will go so far as to say this is not entirely true in larger reality. If you go on to take upper levels of biochem and or organic, you might run across something. They're not common, but it's possible that you might have 4 hydrogens or 5 hydrogens that are lost. However, it's not super, or it's not common in any way in terms of what we see in inorganic chem. So if you have an acid, you want to make an acid-base reaction, we obviously need the other half. And we've seen these, but we haven't really talked about them in terms of them being bases. So again, for this semester, anything that generates or releases OH minuses, all of this is done aqueous. So that's why they all kind of say in water. The two that you see the most often are sodium hydroxide and potassium hydroxide. Sodium hydroxide is the main component of drain cleaner, aka Drano. Potassium hydroxide is the main component of oven cleaner. I will digress for just a moment. We've done things to my house over the years that we've lived here, and one of those things involved stripping some really nasty, ugly wallpaper off of my kitchen walls. And this stuff was glued on in a serious way. So because of, this is what I do for a living, after the first just spray it down with water and all of that didn't work, I started applying a little bit of chemistry knowledge to how to get it off the wall. Because like I said, this stuff was like just glued on. I mean, you would have thought it was put on with super glue. I tried some vinegar, because vinegar is acetic acid, even tried to hose it down pretty well with acetic acid, and it just didn't seem to be going. So I switched gears. I went, well, if the acid doesn't work, how about the base? And I actually ended up using oven cleaner to take the wallpaper off where I couldn't get it to budge in any other way. So there are all sorts of weird and twisted applications for reasons that you might actually use chemistry and not chem lab. One of the things that's true here that you kind of see in the middle of this is the number of H's at the beginning of the molecules need to match the number of OH's from the base. So I gave you one of each here. The first one starts with acetic acid, HC2H3O2. And I matched it up with one sodium hydroxide. So that way the one H that's hanging there dangling out on the front ends up reacting with the OH that is at the end. You get a water molecule, but you also get a salt. Now in this case, it's not salt in like table salt, which is sodium chloride, but it is a salt. Sodium stuck to acetate. Then we look at the next one. So sulfuric acid is the second one there, H2SO4. I've got two hydrogens, so I need two OHs to match it with. I've got two KOHs. I get two water molecules and a salt. Again, this is just a salt. Salt meaning an inorganic compound that is ionic. My two Ks stick to the sulfate part to create my salt. And the third one, we start with three H's because it's a triprotic. There's not a lot of triprotics. Phosphoric is the most common one, H3PO4. I picked a not super common hydroxide just to give you a little bit of variation for the examples there. But I've got three. I've got three LiOHs. I get three water molecules. And again, I'm still got a salt molecule. This one is all of the lithiums that were left over stick to the phosphate that was left over from the acid. So you get a pattern. You have to have one acid, one base, one water, or two hydrogens, two hydroxides, two waters. or you get threes. The 3 hydrogens, the 3 OHs, 3 water molecules. It's a pattern. Again, we're kind of looking at patterning as a way to help you with predictability. Things that you can sort of know that you should be getting as your products. Acid and base gives you salt and water. Now, granted, it's not the same salt. I have various salts shown here, but I'm getting a salt to go with my waters. The other thing that's true, and again, this is one of these things that's kind of, if you take next semester, if you take in second semester chemistry, you get some expansion on this thought. But for the moment, we're going to say strong acid plus strong base gives you a hydrogen ion, an H+, and an OH-, and makes a water molecule. You could do it as 2s or 3s, but doesn't actually change it. You could have 2 H's and 2 OH's give you 2 waters. Back to that whole idea of least common multiple sort of things when you're doing balancing of reactions. If you can make lower numbers all the way across, that's usually what you're shooting for. But it also looks an awful lot like your precipitation reactions, because it's still following this kind of profile of positive thing plus negative thing gives you a product, and the product is neutral because the water molecule doesn't have any charge on it. One of the things that we will eventually get to in lab is referring to this as a neutralization reaction. One of the labs that's toward the end of October involves using the burettes again. And we're going to be doing an acid-base titration that will be using base in the burette to neutralize solid acid crystals. And then we're also going to look at a second version of that where strong base is still in the burette, and we will be using it to neutralize a liquid acid, an aqueous version. So some of the things that get kind of mentioned a little bit in passing here do come back again. Gas generating reactions. And actually, I realized that I didn't take out my reference. I know it says page 140 and 7th edition, and I forgot that that's a reference to a different textbook. Ignore that one. Your textbook is not very great at the gas generating reactions concept. However, it is going to come up in lab because the dry lab, for which I filmed a whole bunch of little mini videos, that's referred to as the metathesis lab, it has a couple of gas generating reactions in it. So this does pop up again. One of the biggest things that you see as we kind of begin to look at these is a whole bunch of these have 3 products, one of which is a gas. So if we look at the first one, we can start with kind of the generic description. Metal carbonate, meaning that whatever metal it was that helped to form this molecule, or a bicarbonate, HCO3s. Add an acid, you get a metal salt, you get a carbon dioxide molecule, and you also get some water as a byproduct. So I decided to pick on the oh so very stereotypical sodium bicarbonate and acetic acid, otherwise known as baking soda and vinegar. If you either did it yourself in middle school, or perhaps you have kids that had to build the volcano, For a middle school project, this is typically how they do it. They add food coloring to the baking soda and then pour the vinegar, and of course it froths and foams and creates bubbles. The bubbles being your carbon dioxide. This is less predictable in that when we looked at the precipitation reactions, we had a kind of a more predictable pattern in going, okay, first one and last one, third and second. This is a little bit messier because you pull out the water molecule, you pull out the CO2 molecule, and then you figure out what you have left. Which in this first one we see the sodium is the metal and the acetate doesn't fall apart. The acetate actually stays intact and becomes part of the sodium acetate molecule. But it's still a metal salt, so you can still follow the pattern. What if you wanted to make H2S? H2S is hydrogen sulfide, the stinky rotten egg smell. If you want to make that as a gas, you need a metal sulfide. No O's in there. You're adding an acid to it. You get H2S, but then you also get leftovers. The leftovers are your metal salt. So the example I gave you for this one has a magnesium sulfide. Magnesium's your metal. In order to make this balanced, I need a couple of molecules of hydrochloric acid. My metal salt is the magnesium chloride. My H2S is my gas. What if I had oxygens attached to my sulfur? That's another variation, but it doesn't give you hydrogen sulfide, it gives you sulfur dioxide. It gives you SO2 as your gas. Your lithium sulfite, lithium's my metal, the SO3 is my sulfite. I've got a couple of HCl's because I wanted to make this balanced. I get a SO2 molecule, I get a water molecule. My leftovers are my LiCl, and that's my metal salt. Beware, don't try to make it Li2Cl2. Mercury is the only thing that likes to do that with chlorides. Now, the last one is a little bit different because it doesn't have acids. It has a base as the thing that makes this happen. Ammonium, which we were actually looking at when I was doing on the board, NH4s. And a strong base. Typically, we're talking sodium hydroxide or potassium hydroxide. Those are the ones that are typically used. The gas you are generating this time is ammonia, NH3. That wonderful smell that like comes up from a fresh litter box. Ammonia as a gas doesn't smell very nice. You also get a water molecule though. Note, water molecules are a byproduct of a whole bunch of these. And I have leftovers making a metal salt. If I take ammonium chloride, that's my example there, NH4Cl. I'm going to use some potassium hydroxide as my base. My salt is the KCl. My gas is the NH3. And then I have the water molecule to account for the other two hydrogens and the remaining oxygen. Like I said, this is not well covered in your textbook. There is some coverage of it in your lab book, but not in really good detail. So this is why it's kind of added in with this chapter, because it's part of the meta thesis lab, which is a dry lab thing that you're going to watch a bunch of videos for. When I did them, and each one is about a minute or so long. They're also all separate. You don't have to like watch them continuously. You can watch them separately if you need to work on your lab in parts. And so I uploaded them to YouTube and then downloaded the links into the lab so you can click on them and watch the stuff being added together and do your observations when you're doing the metathesis lab.
I got a question for you.
Yes.
I was going back to this H2S. Do you actually will you be actually making that in the lab?
No.
Okay, that's a dangerous gas.
Well, and it smells really awful.
Yeah, I almost had a guy die the other day in a manhole because of H2S. So
yeah, no, we talk about it because it is a thing you could generate it, but that's not one we're doing in the lab. Even if we were this lab is actually, like I said, it's a watch the videos lab. But even when we do it for real, that is not one that we actually do.
You smell them in there?
Yeah, if we did it, we'd have to do it underneath the hood.
Yeah, you smell them in manholes all the time. So I work for HRSD. There's some
not pleasant stuff.
No, not pleasant, and it will kill you. Yeah, I just was wondering.
Yeah, no, even when we actually do the lab for real, the semesters that we do it, that's one that we just talk about.
Okay.
Aware that this is how it works, but we don't do that one.
Okay.
All right, let me kind of skim down to a couple more examples here. Sometimes just knowing what category a reaction is some really helpful information. K2CO3, note it's aqueous. Copper nitrate, also aqueous. If I'm looking over then to my product side, I've got copper carbonate, copper 2 carbonate, that's a solid, and some potassium nitrate that's aqueous. One of the big tip-offs here is that everything but one molecule is a solid. And that solid is on the product side. So those are kind of key pieces. You can dig a little deeper and look at it and go, okay, the K's matched up with the NO3s because that's first and last. And then the copper sticks to the carbonate, so third and second. And all of those pieces kind of help you figure out that, yeah, that's a precipitation style reaction. How about a carbonate that's not a bicarbonate? MgCO3. MgCO3 is actually in Gaviscon, which is an antacid that you can buy that's kind of, if you pour it out of the bottle, it kind of looks like milk in color, but it's kind of thick and sludgy because magnesium carbonate is not very soluble, but hydrochloric acid's in your stomach. So if you take the tablespoon of the magnesium carbonate, it turns into carbon dioxide and water, but also magnesium chloride, which is still aqueous, because magnesium chloride is actually relatively soluble, whereas the carbonate isn't. So that one actually is a somewhat real world reaction. So one of the things we've been kind of dodging around is there was a fourth category. We're only going to get through a little bit of this tonight. It's known as redox, which is a contraction for oxidation reduction. I don't know why it's not written the other way. You'd think that they should call it reduction oxidation because that would make more sense since they sort of contract it to call it redox, but textbooks pretty much always list it as oxidation reduction, and then they talk about redox, so it makes it sound kind of backwards. Of course, oxred sounds really strange, or at least sounds really strange to me. So they kind of stick with the redox thing. The mechanism that drives redox reactions is kind of different. Redox is all about electrons. Up to this point, most of the things that we've been looking at are about the ions. Things like copper ions, ammonium ions, chloride ions, and you can kind of mix and match and make molecules out of them. The same is not true about the redox. So brain tricks, oil rig. Oxidation is loss, reduction is gain, which sounds weirdly backwards because your brain kind of goes, but isn't reduction getting littler? But the thing that you are gaining is negative. So here on my desk, I have a box that I throw all my mail into, all my bills. So if I gain a bill, it diminishes my checking account because it's a negative value. So the thing that you are swapping around, they're all negatives because all the electrons are negatives. So it sounds intuitively backwards, and yet it actually works pretty well. If we look at magnesium and oxygen, I know certain things already based upon nomenclature. I know that magnesium, it's an alkali, earth metal. They like to be +2 anyway. So I could speculate, yeah, one magnesium and one oxygen, it gives me a nice neutral molecule. But you have to think about the redox in order to think about the why. Why would this stay stuck together? Well, it's all about the trading of the electrons. Somebody asked me in lab last night about oxidation numbers, which even though they are mentioned a little bit in passing in the nomenclature dry lab, we didn't do part 2A at all, in part because we don't get to this information until now, which is part of chapter 4. Oxidation numbers are kind of like the charges that we've already seen, except it then also gives you some extra options that we kind of took on faith before. We did things like look at the polyatomic ions, things like sulfate, and said, just take it on faith that SO4 is -2. Just kind of believe that for right now. We'll tell you why later. Now we're beginning to get to the why. We've got rules. Anything that is a pure element is considered to have an oxidation number of 0. Here's the why. If you had an atom of silver, that means all the electrons it started with are still there. It didn't give any away yet, and it also didn't steal anybody from anybody else. All of the electrons are still intact, which is why all of the protons and all of the electrons are now canceling each other out, and you have a 0 charge. Oxidation number is kind of sort of a way of giving you charges that may not be, I'll use the word seeable. They may not be seeable because they might be part of a molecule that cancels certain things out. And that becomes sort of a little bit more obvious as we go through these. It also doesn't matter if you have more than one of a pure element. And this is why I gave you 2 other examples here. You could have one of the diatomic molecules. I picked on oxygen. Oxygen as a molecule, O2, has an oxidation number of 0. All the electrons that the oxygen started out with, both of them, are still there. Oxygen is number 8, I believe. So it has 8 protons and 8 electrons. This whole molecule has 16 electrons, 8 for each oxygen. And didn't lose any, and it didn't gain any. You could also do it for something like phosphorus. Phosphorus in its purest state is available as a P4 molecule. Again, if they're all stuck together and they're all just the same element, we assume 0. Now the next one is actually almost just a rehash of stuff we already did for nomenclature. Whatever the monoatomic ion is, its charge is its oxidation state. So if you see a sodium ion, Na+, +1. +1 is its oxidation number. Calcium ions like to be +2s. Therefore, its oxidation number is +2. What about oxygen as an ion? Oxide. It has a -2 charge. That means its oxidation number is -2. Oxygen and hydrogen have rules of their own, of which they each have one exception. So all of the oxygens that are part of other molecules, not talking about the O2 molecule, all the oxygens that are part of other things, we make an assumption that they are their normal -2. Here's the exception. Peroxides, which are actually kind of rare. We saw them just a little smidge in nomenclature. They pop up again here just a little bit. If you have a peroxide, O2 -2, each oxygen is only worth -1. This is what allows you to have hydrogen peroxide, H2O2, because otherwise it would make you think you needed 4 hydrogens to go with the 2 oxygen atoms. But in fact, due to the way sharing is occurring, you actually only need 2 hydrogens to go with it. So one notable exception for oxygens. Same thing's kind of true for hydrogens. Hydrogens are almost always +1, unless you stick it to a metal. Doesn't happen very often, but if you do, then it's a hydride, and instead of being a +1, it's a -1. I think I am correct in saying if you are spelunking and you are going old school and not using an electric headlight, calcium hydride is little gray pellets. And it used to be if you put them in water and they start decomposing and creating hydrogen gas, which burns, a la Hindenburg. But if you burn it at a controlled rate, you can light it, and you can have a little headlamp that is basically emitting hydrogen gas, and you light it with a striker, just like you light a Bunsen burner. And you can have a basically flame set into a reflective mirror-like cup. And that used to be the old school way when batteries were less reliable. If you wanted to go mining, you could use this on your hard hat, as opposed to the more modern version, which is use a battery-powered light these days. But that is one kind of weird sort of piece of trivia usage for this. Fluorine. Fluorine kind of has a special place in a way, because first we start with an assumption, We say if your fluorine is part of a molecule, that means it's with something else, we're going to assume it's -1. Now, that part's not unusual, but it also allows us to begin to look at some of the things that we saw back in the nomenclature when we stuck two nonmetals together and we said, just pretend the first one is positive. This is kind of based upon oxidation numbers. And I went back and I dug up a picture here to insert in my notes. Look at where the fluorine is, that upper right-hand corner there, and it's red. This is an electronegativity table, which is different in terms of the numbers as opposed to the numbers that we usually see on the periodic table. Fluorine is king in the world of electronegativity. Fluorine is the electron pig, okay? It steals electrons from everybody else. It also has a perfect score. It has a perfect GPA. It's 4.0. Everything else is lower in comparison. What electronegativity does for you is it tells you how tightly an atom hangs on to its electrons. So fluorine, being the electron pig that it is, hangs onto its electrons super, super tight. As you go back in the other direction across the periodic table, it becomes easier and easier to steal electrons from things as you go back toward the left-hand side. You'll note if you look on the left-hand edge of the table there, with the exception of hydrogen, which kind of has its own thing going, all the other ones have quite a bit lower number values. 1.0 for lithium, 0.7 for cesium, so they're all kind of small in comparison. Later, this will circle back around and we will use electronegativity again in a later chapter, but it's introduced the first time for this chapter. Last couple of rules. If you add up all your oxidation numbers for a neutral molecule, they should be 0. They should total to 0. Now, that's not anything any different than we did for nomenclature. For nomenclature, we said, make a match, make sure that all your positives and all your negatives cancel out. But the final rule is for things that are not neutral. And the things that are not neutral that we see the most often are polyatomics. Back to sulfate again, because sulfate's a nice common one. Sulfate has a -2 charge on it for that group of molecules. As we progress toward the end of the chapter, which is mostly a Thursday thing, you'll see that as you're adding up these numbers, there are leftovers. Things that don't cancel out. So like I said, this is digging deeper into the why some of those polyatomics have the charge they had. Because originally we just said, yep, memorize it or look it up and just assume that it is what it is. Now we begin to learn why they bond together the way they do and why the charges on those polyatomics turn out to be the way they are. This gets us about 60% or so through the chapter. We still got a little ways yet to go. We have stoichiometry up and coming, but that's not a today topic. All right, so I'm gonna kind of stop there today and pick up more with the further adventures of redox on Thursday. Questions about the redox? I may do a little bit of the board stuff on Thursday again to show you one of the super messy redox reactions. We're going to have a look at all of the charges on a whole bunch of different elements, kind of that are all combined in one reaction. And I might do that on the board because it's kind of easier to draw all the arrows.
I got one question.
Yes.
When going back to the beginning, we was doing what we was doing the base, doing the acids and stuff like that.
Uh-huh.
You pulled out the hydrogen, and we're doing a full method trying to follow. How do you pull out the H2O?
So the H2O is the H that came from the hydrogen combined with the OH from the base.
Okay.
You take the front end of one molecule and the back end of the other molecule and you stick them together, because we could write water HOH. We don't write it that way usually, but you could. It wouldn't actually be wrong.
I got you. That's it. I'll try to figure out where did you pull that from, but now that's it.
Yeah, so front end of one, back end of the other, stick them together and make a water molecule.
Got you. Thank you.
Other questions? This is a very, very information heavy chapter. I will tell you that the test for chapters 3 and 4 combined, statistically speaking, is the one that people tend to hate the most, because it's a mixture of things like empirical formulas and percent by mass combined with reactions and stoichiometry. So there's a lot of information there. I'm trying not to load it onto you all at once. We're trying to space it out a little bit and go over some stuff and give you semester examples and things like that. And some of you I will see, actually, most of you I'll see on Thursday, and then some of you I will see for the next lab upcoming on Monday, which should be the hydrate lab. We have now finished what I will call as the second rotation, because the first pair was dry lab 1 and experiment 1. That was the first rotation. The second rotation was dry lab 2 and separation of a mixture. And I think everybody's, because the Monday people, as Monday people, we are out of sync because of the whole Labor Day thing. I think everybody has been through, even if you don't have me for lab, I think everybody has now, I believe, successfully completed the separation of a mixture lab. So this coming week, we start the third rotation, which is metathesis and hydrate lab. Those two. So the hydrate one is the in-class one. The metathesis one is the one where you look at all the pictures. There's 8 pictures because there's 40 little tubes to look at. And I put them in pictures that are 5 apiece. And then there's 11 reactions. And I filmed each of the 11 reactions, and you watch them, you write down your observations, and then later you go back and you write the equations for them. All the things we've been covering the past couple of class periods, last Thursday and today, are all kind of key features to writing the reactions for the metathesis lab. Just try to keep everybody in the loop if at all possible. Questions? I know it takes a while for it all to kind of soak in. All right, well, send me questions if you get jammed up, and otherwise I will see you on Thursday.